Okay, welcome grade 12 chemistry students. Today what we're learning about is Hess's law the short way. We're going to solve some problems, okay? So last time we learned the long way, this time we're learning the short way. We're going to use a little bit more math. To do Hess's law the short way, what we need to understand first of all is something called the heats of formation. And heats of formation is when 1 mole of a compound is produced from its elements. In their most stable state, the quantity of energy which is involved is called the heat of formation, and it's given the symbol delta H with this little, again, degree sign, which means STP. So that little degree sign there means STP. So, for example, in order to understand the equations for formation, we have to know how to write them. So to do this for H2SO4, we have to write it as it's coming from its most stable elements. So this is actually what it would look like. H2SO4 is composed of hydrogen, H2, sulfur, S8, its most stable form, and oxygen, its most stable form is O2. Now all we're doing in the front here, I'm circling the coefficients here, we're just putting them in the front so we can balance it out. Now you may be wondering, particularly, you should know why H goes in twos because it's diatomic. So is oxygen, but sulfur is most stable as S8. So we'll do a couple more just to make sure that you're familiar with this. So write the formation equation for carbonic acid, H2CO3. You pause the video and see if you can do that now. If you did it correctly, what you should have is H2CO3 is being formed from H2 plus carbon plus 3½ O2s. Let's do one more. So pause the video and do it for perchloric acid, which is HClO4. So pause the video and see if you can do it. And again, if you do it correctly, what you should have is half H2 plus half Cl2 plus 2O2 equals HClO4. Now, we can actually use this heats of formation to find an equation involving CO2, H2O, and H2CO3. So for example, if I wanted you to find the enthalpy for this reaction, what could we do? Well, if you look in your textbook on page 799 to 800, there's a whole bunch of values that you're given. Okay, so this is our equation that we want to find the enthalpy for. And if you look, there's an enthalpy of formation for CO2. Okay, it's in this value, negative 394, is actually found in that page 799 to 800. It's also found in the periodic table booklet that I give you in class. And we also have the heats of formation for H2O. So far we have the heats of formation of this compound. It's just made of its elements. Gives us a value from the back of the textbook. Similarly for H2O, similar, yep. And we also have something for H2OCO3 in the back of the textbook. So we want to find, recall, we want to find the enthalpy for this reaction at the top. To do that, what must happen is we're going to rearrange these three equations just like we did Hess's law the long way. Okay, so right now we're doing Hess's law the long way. So we want to, again, flip equation number 2, so H2O is on the left side, it is a reactant. We also want to flip equation 1, so it's also a reactant. And we want to leave equation 3 alone. So again, we're just going to change the sign for 1 and 2 and add it to 3, and we get a delta H value. Okay, so if we add them together, flipped, 2 and 3 are flipped now, add them together, and we get negative 20 kilojoules. Now, this is fine, but there's actually a faster way to do this. And the equation is the following. So this is Hess's law, the short way, and it's actually an equation. And what it says is the heats of formation of any reaction, or sorry, the enthalpy of any reaction is equal to the sum of the heats of formation of all the products minus the sums of the heats of formation of all the reactants. So for example, we can find any thermochemical equation. If we want to write it, what we have to do first is we have to write a balanced chemical equation. So let's actually combust methane gas. So methane gas combustion is methane plus O2 equals CO2 and water. We balance it first. Then what we're going to do is we're going to use our equation. Okay, so we are going to find the heats of formation for every single chemical that we have here. So we look on our table on page 799 or in our periodic table booklet there, and we look for the heats of formation of each one of these. We want to make sure that we're specific If it says gas, we're looking up gas. So what we do is, again, we actually multiply the heats of formation for my product. So for CO2 gas, it's negative 394 kilojoules per mole. We happen to have 1 mole in front of it, so we multiply it by a mole. Then we add it to the heats of formation of water, liquid, which is 286 times 2. So this is the heats of formation for all my products. And I'm going to subtract that from the heats of formation of my reactants. And if you take a look for methane gas, it's 74.9 kilojoules times 1 mole. And the heats of formation from anything made up of its elements is actually 0. Okay, so that's why this is a 0 here. It is 0 kilojoules per mole. You multiply it by 2. If you take a look, this actually should have a 2 here when it's balanced correctly. So that's actually a mistake on my behalf. And when we add that all up, we do some algebra, and we get an answer of 891 kilojoules. So let me do an example for you on the piece of paper. I'm going to write it all out, and we'll see if it makes sense. So this example, what it says find the enthalpy for the combustion of butane. Write the thermochemical equation. So what we're going to do first is we're going to write a balanced chemical equation for the combustion of butane. So I've just balanced it out there, and we have butane, which is C4H10. I balanced my carbons, 4 carbons on both sides, hydrogen, 10 on the reactant side, 10 on the product side. I added up my oxygens. I had 13 oxygens on 13 oxygens on the right side. So therefore, on my reactant side, it was 13 times 2 divided by 2, so I have 13 on this side. Now I need to get a heat term in this spot here. So what I do next, and I would write this down, is I'm going to find my enthalpies for formation for each one of these chemicals. I'm going to write it down. Now if I'm going to do the heats of formation, I actually have to know if it's a gas or a liquid. And oftentimes when we're doing combustion, we assume that it's hot, so it's going to be water vapor. So we have gas O2, gas CO2, gas H2O. I'm going to write down the enthalpies of formation underneath these chemicals. So these are all my heats of formation. So my molar heats of formation for all my reactants. I got this from the back of the textbook or my periodic table booklet that we have in class. So since we haven't been given any sub-equations to add together like Hess's law the long way, what we're going to do is we're going to use the heats of formation in this equation down here, which is the enthalpy is equal to the sum of all the heats of formation of the products minus the sum of the heats of formation of the reactants. So this is what it will look like. I'm going to substitute my values into the equation, and I'll explain it to you as I do it. So delta H. So what we're going to do is we're going to do a big square bracket for all my products. And we know that we have, my first product is going to be my CO2. So I'm going to go put my heat for formation for CO2. I'm going to include my units. That's right. Include your units, people. And multiply that by the number of moles that I have. Okay? So this is for CO2. And then I'm going to add that to what's going on with the H2O, which is negative 286 kilojoules per mole times the amount of moles that we have of water, which is 5. Okay, and then I'm going to close that off. I'm actually going to put each individual one in a circular bracket there, just to keep it organized. And that's all my information for my products. So then I'm going to subtract that for all my reactants. So the first red bracket there was the heats of formation for my products. Now I do my reactants. So we have, if we look at butane, we have 1 mole of it, and the heats of formation of it is negative 126 kilojoules per mole times 1 mole. And then we're going to add that to the heats of formation of O2. But hey, look guys, it's already in its elemental form. It has a heat of formation of 0. So that is not going to do anything at all to our equation. So we can multiply that by 6.5, but again, that's irrelevant. Now take a look at how all my moles will cancel out in every single one of these, so that when we do our algebra, our answer is going to be in what? That's right, it's going to be in kilojoules. So let's do the second line. Let's do a little bit more algebra for you guys. Here we go. So by doing a little bit of algebra, we got 3006 kilojoules for our products and negative 126 for our reactants. When we did that work there, we add that together and we get negative 2,880 kilojoules. That's right. That's how many kilojoules we get. We have to put that into our equation. If we take a look, that's the enthalpy of formation for this reaction. Since we put all our coefficients 1, 6.5, 4, and 5 into this equation, we end up getting this amount of enthalpy for it. And notice how I have a negative, so therefore I know it's exothermic. If I want to include it in the thermochemical equation, I turn it to a positive, make it on the product side, and that's the answer, folks. Hope you enjoyed that. We're going to do a couple more of these examples in class. I hope this makes sense. That's Hess's law the short way.
Oh, please, don't you rock my boat.